So we are going to start a topic named Reynolds Transport Theorem. And what I could say, this is some kind of a difficult derivation. Most of the students will start to feel that if they see this derivation in any textbook or anywhere else or in any other sources, obviously the thought of students will be seems to be difficult, okay, at the first approach. But once we start digging deeper and once we start knowing the real concept behind it, it's actually very simple. But to be honest, this is compared to other topics of fluid mechanics, this Reynolds transport theorem derivation is bit dry, okay, comparatively. But at the same time, it's not tough, okay, it is easy. Okay, so just be with me until the starting and until the end. Okay, so my approach, I'm going to do it in a manner such that you can understand it in a much better way. Okay, right. To start with, first of all, we need to understand why we need this Reynolds transport theorem. What is the significance of this Reynolds transport theorem? What it is going to do? For understanding why and what actually this Reynolds transport theorem is going to do, for understanding that, we need to know the basic difference between control volume and system. I already discussed about the system and control volume in the basic thermodynamics, right? In the first chapter, obviously in the third video or the fourth video, I would have talked about basic difference between system and control volume. But now, let us keep that aside, okay? Let me just bring a fresh thought here and then let me just recollect it, okay? Right, so first of all, what is a system? System is a region or a space, or I could say that bunch of molecules or fixed mass, okay, so we can call it in a different way, okay, so if I say that it's a system, okay, region of fixed mass, okay, or what I could say, it's molecules, okay, bunch of molecules combined together, or fixed identity. What is mean by fixed identity? It's something like if I take this as my what is that? If I take this as my system, it contains different molecules, right? Bunch of molecules, bunch of identities, right? So all together is taken as a single, what I could say, all together is considered as a system. And for doing the analysis, okay, if I'm going to do the analysis or if I'm going to study, I'm going to focus on this bunch of molecules, or you can take a bunch of molecule or you can take a single particle also, it's up to you. Okay, bunch of molecule or bunch of fixed identity, fixed mass. The fact here is I should not change the mass, I should not change the identity. This molecule has to be this molecule only. So when I'm starting the analysis, I need to fix this, and until the end of my analysis, I need to fix this only. So that is why it is fixed mass or fixed bunch of molecules or fixed identity. It's not going to vary until the beginning, from the beginning until the end of our analysis. Okay, right. Now, I can give some examples, some of the basic examples which I already given to you when I'm discussing basic thermodynamics is the piston cylinder arrangement, right? So this is our fixed mass. Okay, I will just fix some mass. This is my system. Of course, this is my boundary. Okay, so here if I do a compression process or if I do an expansion process, so I will be fixing this mass. Okay, so I'm not going to change the mass. Either I will be compressing it or I will be expanding it. But if I compress or if I expand, the boundary may change. You could understand that the boundary may be flexible or it may be fixed. For example, if I take a rigid container and if I take all the molecules, all the combination of masses which is present in a rigid container as my system, boundary is fixed. There is no expansion of boundary or contraction of boundary. But if I take an example of piston cylinder arrangement, of course the boundary is also going to change. So one point to note in the system is boundary can be flexible or like flexible or movable, or it can be rigid also. It depends on the particular system. Okay, a basic introduction of a system. But now just think about this case. Will it be that much easy for us to analyze by fixing a system and doing the analysis? It is very simple in this case. If I take a piston cylinder arrangement, control mass, that is this system, approach or the system is also called as control mass. Okay, so if it is a piston cylinder arrangement or if it is a rigid container, control mass approach is it is comparatively very simpler, but is all the flow process, okay, because we are in fluid mechanics. So if you consider fluid is flowing through something, will it be convenient for me to do my analysis by using system approach? See, just think about a situation where aeroplane, okay, so a plane, and air is flowing over the plane. Will it be convenient for me to focus on a particular system? Okay, aeroplane is there. Let us consider this is the aeroplane flight, just moving in this direction. Will it be convenient for fixing my air? Okay, these are my air molecules where I am going to concentrate. Will it be convenient for just to focus on this air, wherever this air goes? Okay, wherever this air goes. Will it be convenient for me to focus only on that air molecules, that is my system control mass approach? It's not going to be that easy. Or I'll just think about very simple example, fluid flowing inside a pipe. Fluid flowing inside a pipe. I will give one example. Listen carefully. Suppose I'm taking, let us consider this is the pipe, okay. Let us consider this type of pipe was there, okay. Let us consider this is the ground where the water is stored, okay. So now I am fixing some molecule is entering our pipe, okay, some molecule is entering our pipe. Now I am going to fix those molecules, okay, bunch of molecules. I am going to fix the mass, okay. So this is my system, and this is happening at time is equal to 0, that is at the initial stage, okay. Something you can consider, I am having a pump and I am pumping the fluid up, okay. So at time is equal to 0, this is my system. Now as time increases, maybe we will consider after some 40 seconds or 50 seconds, this will reach here, okay, my system will reach here, okay, my system after time some 40 seconds, after some 20 seconds, my system is reaching here, time is equal to some 60 seconds, again here after some 90 seconds, here after some 120 seconds, and finally after some 3 minutes or something like that, my molecules are coming out. And now that I can just imagine that these are my system molecules, which is like after some 180 seconds, okay. Think about this situation. Will it be convenient for me to focus only on this and start doing my analysis only on this continuously? Can I focus? Can I do like that? I'm focusing on this particular system and I'm continuously doing my analysis. I'm continuously doing my analysis, and finally my system is coming out. Will it be convenient for me? I will give another one practical example. Just imagine that water heater in your bathroom. Okay, so water heater. If you want to analyze the water heater, will you do this? Will you go to the tank? Okay, the tank where the water is stored. From there, you will fix a small quantity of mass, and will you start analyzing that mass from the tank? Okay, from the tank, wherever it is flowing through the pipe. Maybe the tank might be there in the top floor. From the top floor, you have to fix a particular mass. Okay, you are fixing some particular bunch of molecules, mass, and you are focusing only on that mass. Wherever it goes through the pipe, you are focusing only on that. And finally, it is entering the heater. It's flowing inside the heater and it is coming out of the heater, and then again you are focusing on that until it goes to the sink. Will it be convenient for me to do this? Will it be convenient for me to fix a molecule or fix some mass and to follow that everywhere? It's not convenient if it comes to fluid flow problem. Yes, it will be convenient in this case, of course. A piston cylinder arrangement, yes, it's very good, well and good. But these types of flow problem, it is not convenient. So what actually you will do in case of water heater in your bathroom? How you will analyze? Very simple. If this is my water heater, okay, if suppose this is my coil, simply what you will do, you will consider how much mass or whatever, okay, whatever thing which is entering here, okay, whatever property which is entering here, and how much it is leaving with. So I am not going to worry about the mass, or I am not going to worry about the identity. I will just focus on what is entering, what is leaving, and this area or this volume, okay, this volume where you are focusing, where the molecules are entering and the molecules are leaving, that is called as control volume. So in case of control volume, your volume will be fixed. Okay, the space will be fixed. I'm not fixing mass. In this case, I'm fixing the mass. Wherever the mass goes, I have to move. In this case, I'm fixing the space. I'm not varying the volume. Okay, so if something enters, I will see what it is entering, and if something leaves, I will see what it is leaving. I will do the analysis. I will fix my analysis with respect to this particular volume. Okay, so that is my control volume. Here, space is, or I could say that volume is fixed. Okay, space or volume is fixed, where our complete analysis will be done. Of course, for example, in this case, what I will do, suppose I want to do the analysis on this elbow. Okay, I want to do the analysis on this elbow. So I will fix that particular volume only. Okay, so this will be my control volume, and the surface or the boundary, okay, the boundary which is the surface of the control volume. Okay, so that our boundary is called as control surface. Okay, so generally CV implies control volume and CS implies control surface. So note it down. Hereafter I will be using CV and CS only. So instead of focusing on this bunch of molecules everywhere which is flowing over the pipe, if I want to do the analysis only on the elbow, I will just fix the volume on the elbow. Okay, so that is my control volume, and the surface which is bounding the control volume is my control surface. Very simple, right? So that is what the difference between control volume and control surface. And most of the cases, control volume's boundary will be fixed. Most of the cases, but in few cases the surface might vary. For example, consider an aeroplane. Okay, I given the first example, right? So plane which is moving. In this case, what I will do, suppose if you consider, so let us just take an example. If suppose this is a plane, what will be my control volume? This total I will be fixing. Okay, this will be my control volume, this will be my control surface. So here in this case, the control volume itself will be moving, but in most of the cases, control volume will be fixed and control surface will be fixed, something like this. Control volume will be fixed, control surface will be fixed. But in few cases, for example, as a given plane, where I will be fixing my plane surface as my control volume, so wherever the plane is moving, we also have to move. But those are some specific cases. But most of the cases, especially in the fluid flow inside a pipe or fluid flow in somewhere, okay, where the fluid is flowing on something, we will be fixing the position. Okay, something like this. We will be fixing this position, we will be fixing this space. Okay, I will be fixing the space, and whatever is entering, whatever is leaving, I will do my analysis. Okay, that is nothing but my control volume. This volume is control volume, and the surface which is operating is control surface. Now, which one is convenient? Which one is easy? Of course, the easiest way or the convenient way is the control volume approach, right? See, you could relate this exactly. Okay, whatever I discussed now, it's exactly what Eulerian and Lagrange approach. So Euler used to follow control volume approach, and hence it is Eulerian. I already discussed about this, but I just want to recollect it because this RTT, Reynolds Transport Theorem, has one important significance which you can understand only if you know this control volume and systems difference properly. Okay, now let us continue. So this control volume approach is nothing but the Eulerian approach, which has been already discussed, and this system approach is something which is Lagrangian approach. I will be fixing a part of molecules, or I will be fixing a single molecule, and I will be following it everywhere it goes. Okay, now comes the important point. So I hope that difference is clear, what is system and what is control volume. Now the important point is, most of the physical laws, what is mean by physical laws? The best example which I could give is Newton's second law of motion. Okay, Newton's second law of motion, or whatever the laws which you are studying in your engineering mechanics, physical laws. Okay, so basic mechanics, and all the physical laws are defined for a system. I will give a simple example. Okay, just consider a car is moving on some road. What is the, if you want to find out force, or if you want to find out the, what I could say, acceleration or something, what actually you will do? Summation of forces is equal to mass into acceleration. And I am doing this for what? I am doing it for the car, right? I am doing it for that car by treating the car to be a particle system. So here my car is the system, or that car is the particle. Again, it's a particle approach or system approach. And similarly, whatever you take, this is the best example, a simple example. A man is walking. If you want to find out acceleration, I will be fixing the man only. Okay, I will be fixing the man and I will be finding out the acceleration. So all the physical laws, Newton's law, force is equal to mass into acceleration, other laws, Euler's law also for rotational motion. Okay, so everything is given for fixed mass case, that is system approach. Okay, all the physical laws are available already. Physics has given us all the laws for fixed mass. But as we know that fluid mechanics is not something which can be easily studied by considering a system. Okay, because we know that I already explained it. So it's not easy for us to study by considering a system. So it will be always convenient for us to fix the volume, that is control volume. So now this Reynolds Transport Theorem is something which is going to link, okay, which is going to link everything from the system with the surrounding. For example, mass conservation, momentum conservation, energy conservation. Basic, right? Mass conservation means what? Just consider I am taking, you can consider a container. I am filling a mass inside. My container is my system. So what is the mass conservation? The mass cannot go out, the mass cannot come in. So it's fixed. Okay, m is equal to constant for the system. It is something which is very, very intuitive. Okay. Similarly, like mass and also the energy conservation, energy can be neither created nor destroyed. Again, that is also defined for a particular system. So everything is defined for a system, but now I need to talk with respect to control volume. Okay, so what I'm doing here, what RTT is going to do, it is a link. Simply, it is a link between system, whatever the law which I defined for system, with the law of control volume. So from the law which is defined for system, I am finding it for control volume. Very simple. I hope that it is clear. Okay, so the significance of RTT is this only. Physical laws are defined for system. Now I am going to convert that physical laws which is defined for system into what is that, for a control volume. And the major example which we are going to do is mass conservation, momentum conservation and energy conservation. So we will start the derivation. Actually it's a bit big derivation, you have to be patient with me until I complete this.